once I've got
third lecture of this mini course. Very interesting mini course. Thank you very much.
So this is a bit misleading. There's not going to be very much geometry in this slide. Just for the fun of it, I don't know if any of you know Sasha Borovic. He's originally a group theorist and geometer of some sort, but then with Poisson, they really developed this the theory of algebraic geometry, and Pushkovsky's behind all of this, but and this is a book. Sasha has various interests of the kind that we have, and this book is talking about how mathematical concepts develop in a very episodic way. He goes through with various kinds of mathematical things. The start is Euler's problem about reflecting mirrors. And he says, well, this is a very basic psychological thing. You can see this. But then when you put it in the mathematical context, just something you may want to look at. I'll have it here for a while afterwards, and then people can find it. So most of this will be about the use of inferential logics, which is, as we say, so what we're trying to do is think about categoricity, largely in response to Button and Walsh, but also just in general. And what we are going to prove is we're going to find an extension of omega of first order logic plus a rule. And with that, and we do that in both a one-sorted situation and a two-sorted situation. In the one-sorted, you get things like Robinson's Q is categorical. The only model is the standard model that we think of. And in the two-sorted version, you can encode L omega 1 omega, and so we'll get a categoricity of something that arguably is what Euclid really was thinking about. Not convincingly, but arguably. Okay. So this started because Constantine had a paper in the JSL, or Bull to BSL, I think, in January of 24. And he talked about categoricity of a logic, or categoricity of a logical rule. And what in the world does that mean? And it turns out that, and I learned this word polysemous just because I wanted to have something that meant this, and I worked backwards and found it. Polysemous means a word that has many meanings. And categoricity, in Dedekin's sense, is exactly one model. In a model theorist sense, it's categorical in some particular cardinality, or hopefully many cardinalities, and that's the whole name of the game. And thirdly, in this school of inferential logics, it means the logic is categorical in the sense that the syntactical rules completely determine the semantics. Now, does anybody here know about this? I asked this question at Notre Dame, and Curtis wasn't in the room, and so nobody answered. But we'll see what that means in a minute, because it's a strange thing to me. And then, so we're going to be talking about 3 different cultures. A little bit that influences. One of these is model-theoretic logic in the sense of the book from the early 80s. One of them is model theory, the normal way. The difference here is that quantifiers come first, right? And you may or may not have syntax and rules of inference. Here, I mean, you definitely have syntax and rules of inference. And inferential logic insists on the rules of inference, and then you develop some semantics. And as far as geometry is concerned, I'm going to be using several logics, and I've kind of separated them. That is the logic of L omega omega, but you can think of it just with congruence as the basic notion, which is what Hilbert and Tarski and Euclid are doing, or with distance, which Hilbert defines, and so that now makes sense. Or Birkhoff or Gua, who I'll talk about a little bit. I think I talked a little about them yesterday, who build distance in that's one of the basic relations. And then the 2 inferential logics that I'm going to explain to you today. And L omega 1 omega, and then second order versions. And the difference, of course, that Hilbert's first 4 axioms, 4 axiom groups are first order. The second is, well, is a combination of L omega 1 and second order. And what our basic relations are going to be central in all of this. And of course, that's the model theoretic standpoint. And in a certain sense, it's irrelevant in second order logic because you can define anything you want. You've got set theory as part of your basic structure, so. Now, completeness also is polysemous because we have what Hilbert was grasping at in 1899 and was made clear by Frankel in the middle 20s of categoricity as having a unique model, and then completeness in Gödel's sense of truth equals provability, which interestingly, that phrasing seems to stem from Robinson in the mid-40s. It's not the way people were thinking about it in the 30s. And yeah, and what we do here is you have the sort of basics of Euclidean geometry. You define the field, and then you can determine the complete theory by fixing the first order theory of the field. And whether you can do that for complex, see, it's an ordered field, and whether you can do it for an unordered field is something I've thought about off and on, but right now I don't know how to do it. Oh, so this is what I just said. Okay, I got ahead of my notes. Okay, and now making distinction, the Archimedean axiom is certainly not first order. It's an L omega 1 omega axiom, and it's really about an ordered algebraic structure. I mean, semi-group maybe would be enough, but you don't. There's a related notion in terms of orders, which is widely studied, but it's not quite the same thing. All right, and just how it's used in Hilbert, Archimedes is used mostly for providing counterexamples. That is, for saying, oh, here's this axiom that I want to show is independent, and Well, it's independent because it's not true unless you have the Archimedes. And then in the last, he has 3 or 4 pages where he proves categoricity, and there he uses Archimedes, which he doesn't really have to do because a complete ordered field is automatically Archimedean, which I suppose Dedekind knew that, but I don't know. Maybe it didn't get formulated later. We have this the sort of the underlying thing here. When does the concept show up? Right, and that's, I mean, yes, so this is again just an aside, but Hilbert's definition, Hilbert's completeness axiom is that you have a maximal model. That the structure we're looking at is a maximal model. Now, as Van Anen has pointed out, that's not a second order axiom either, because you have to say for every model something is true. And so there's something called sort logic that allows you to formalize it in the way that Hilbert stated it. But for our purposes, just using the second order axiomatization of the field, and then that gives you the Archimedean is essentially the same thing. Okay, and I think, well, yes, so I have just said in looser ways what's on the slide. Okay, so what I'm going to do is provide something. Oh, no, there's no other place here. What have we been doing before? Oh, I see. Yeah, I just worked, right. Yeah, maybe, yeah, I think it was in over there. Yeah, I think that's really all we have to do. I'd forgotten about it. Well, no. Yeah. Oh. Oh, yes, okay. Well, that didn't seem to help. I think it's just easier to, yeah. Okay, so I'm going to introduce these inferential logics, and before that, I'll explain what it means about being categorical in the inferential logic sense. And because we're talking about the logics will continue to have the downward Lowenheim-Skolem theorem. So when I say something's categorical, it's going to imply that it's countable. So the reals just are not going to show up here, or if I get a categorical theory of geometry, it will be the some countable field. Okay. All right. So I think we've sort of done this before. Logic just you have certain logical operations, and if it's an inferential logic, you have rules of inference. And then there's this kind of parallel development in inferential logic. You have a collection of sentences, and you have a valuation assigning truth to each of them, or truth or falsity to each of them. And that's the basic notion. And in model theory, you have the notion of structure as basic, and you define by induction truth in a structure. Now, what we want to do is try to find a way to make these two notions connect. And so evaluation is what I just said. It's permissible if it takes values on all the quantifier-free sentences. So this collection of sentences has to tell you all the quantifier-free sentences. The resulting set of sentences is consistent, and it preserves the soundness of the inference rules for identity and the axioms that we'll later prescribe for propositional logic, because this failure of categoricity for propositional logic, it fails for propositional logic in the way that most people think about it, and that's been known for 75 years. So the point is that what I've done with a permissible, by defining this notion of permissible, I have given a way to construct a structure in the model-theoretic sense. And so by restricting to permissible valuations, I've got just two ways of describing the notion of structure. Right. And sort of the key point about this is that if you take any permissible valuation on a particular tau structure, it'll give you the same truths for the quantifier-free formulas. Now, an inferential logic has a set of rules of inference governing the logical operations. And the model of this field is the meaning of the logical operators is given by the rules of inference. So now we have one more strengthening of the notion of a permissible valuation. It's admissible if it preserves the soundness of the relation of logical derivability with respect to the rule R. Right? So really, I should say admissible for a set of rules R, if each rule in R is sound, and it's categorical if you take any countable vocabulary, all admissible valuations, then the meaning of the truth is what we normally think of. Here, the Robinson-Tarski kind of notion. It doesn't imply Gödel completeness. And in fact, one of our questions, we don't know whether the logics we're talking about are Gödel complete. They probably aren't, but we don't know. All right, so for and, everything's hunky-dory. Well, that's probably too British, too American. It goes well. If you say from the and rule tells you, the and introduction says if you have phi and psi, then the conclusion is true. And elimination says you can drop to either phi or psi. And then this gives you that phi and psi is true if and only if they're both true. But the same set of rules for psi are not categorical. You don't have enough. I mean, so well, it's not even the same set of rules. They're because people realize there's a problem, they have some strengthenings. And so something like, if you can prove psi from these premises, then you, from one of these premises, then you get it. And this is, I think, Carnap's example. Might have been somebody earlier. There is a standard valuation over the propositional logic that makes a disjunction true, although both its disjuncts are false. Anybody seen this? No. So it's that let us call the valuation of a formula true if it's provable. And now you take a formula that's neither, what do I want to say? Not independent, but did I have something down? Yeah, well, yeah, not decided, but there's another standard word for this, something that is both it and its negation are consistent. Anyhow, if you take such a thing, then clearly both of them are false because they aren't proven, but the disjunction is true. Now the question is, now I don't know why I haven't said, maybe I'll say it in a minute, but there are ways out of this which are known since the 40s, and we're just going to assume we've fixed a set of propositional rules that do that, and we aren't getting into it here. But now what about quantifiers? Well, the standard way of dealing with universal quantifier introduction, well, the introduction is if you have a free variable proof of T, where T is not involved, right? Then you conclude for all xt, and for all x phi of x, you conclude phi of any term. Now, Carnap has this example of why this is not categorical. So my vocabulary has two unary predicates and a countable number of individual constants. And I'm going to take some standard truth theoretic valuation, and so it will mean that if we write v of for all x f of x equals true, we want to say that's true if and only if, the standard one does say, right, if v of it's for all x f of x is true if and only if for every substitution it's true. But now define a valuation v prime that also maps onto the countable set of objects and agrees with v on the quantifier terms. So it makes the same things either red or green or both or neither. But the new valuation says v of f of x, v prime of for all f of x is true if and only if it is true for any particular, it's in f, all constants are in f, but in addition, some c must be true. We fix a c and it's got to be true. Well, but now this has, these are different things that are models. And so the notion is not categorical. I have two valuations that are both sound. I mean, maybe this is the point that the soundness. I have to prove that second v prime is sound. That's what gives us the contradiction. And if this counterexample B happens to be both red and green, or whatever there was, then we're fine. But if it's false, but then the thing is sound because for all x f of x isn't true. And yeah. Looks to me like I've just written the same two. Oh, that also works. I mean, I have to show that both rules are sound, but both the elimination and the introduction. So that's the two sentences doing that. And so, since it satisfies the soundness of both the introduction and the elimination rules, it's a non-standard valuation. Now, Carnap has gotten around this in the 40s, but I'm not sure if I say this a little later, but in a way that it was that it's on the face, the way you write down the logic, every model is countable, and we will avoid that, and so it's different. Yeah, so this sort of says what I mean. We're going to use these appropriate multiple consequence rules for the propositional logic, and we're going to add a new axiom yeah, this is what I just said right now. The problem with this was models, all the models are countable. We don't want to have assumed that before we start. And so our fundamental semantics is Robinsonian. When I give you a structure, I add names for all the elements of that structure, and then I have the valuation, or the very definition tells you what sentences are true of the constants, and then you build up by induction. I mean, so this, and that's, may come back later. This is the definition in the first few pages of Button and Walsh. And then we're going to talk about various omega logics with something in front of it to say what version of the rule we use. Well, the classical omega rule you have a collection of constants, specified set of constants. Usually they say the numerals, and you know, this of course is coming out of the study of arithmetic, and so the C's are automatically the elements of the natural numbers in the one-sorted system, and we'll come to the two-sorted in a minute. And the classical omega rule is, if it's true for each one of the constants, then for all x phi is true. And this is any well-formed formula of the vocabulary that we've started with. Now what's going to happen is we're going to modify that part a little bit, and that makes all the difference. Okay, so our inferential rule is the same, but we may have parameters d. When you've taken this bigger model, you've expanded the language. So you have allowed to have some constants beyond the ones that are fixed, right? And you say, if the I omega rule says, if for something even with this additional constant, if it's true for these standard constants, right, then you deduce for all x. And the universal elimination is the same as usual. But again, it allows that extra parameter. Right, and now we want to prove that logic is, or that rule of inference is categorical. So this is the inferential logic theorem. All right, if you have an admissible valuation, if this is, so looking first for the if the universal statement is true, then all the constants are true. Well, this is just exactly the I introduction rule. Right, that means the for all introduction rule. And on the other hand, saying that if it's true for these particular constants, then it's true for everything, is the omega rule, is our general, or we call it the inferential omega rule. So now I'm just going to give a little notation we've been using the word omega structure all week, but there's a difference whether you have a one or two sorted structure where you're thinking about it. And so in the one sorted case, we want to insist that these constants name everything in the universe. But in the two sorted case, we have this predicate n, and we're only worried about naming every element of n. And this is basically Henkin and Uri in the 50s, and and it's a theorem of them that a theory is omega consistent if and only if it has an omega model, which is another, for model theorists, it's another way of saying the omitting types theorem. And now a definition that we're going to use, and it's less common, is I say a structure is an algebraically or Robinson prime model of T if it can be embedded in every model of T. And I have to emphasize that for model theorists because we automatically think it's Vought prime. It's an elementary submodel. That's not what we're asking here. We're only asking that it can be embedded. All right, now by Robinson's Q, and what, this is Raphael Robinson, right? He gives a finitely axiomatizable theory in the language with successor plus n times. He does this for the purpose of getting the incompleteness result in a finitely axiomatizable language, finitely axiomatizable theory. And what I'm going to prove on the next slide is that Robinson's Q is categorical if we add this omega rule. Under the ordinary omega rule, I haven't thought about it, but the ordinary omega rule gives you true arithmetic, but you haven't destroyed the structures. You still have uncountably many countable models. But if we take any model of Q, the substructure generated from 0 by these operations is exactly the natural number structure, the algebraically prime model of arithmetic. And so an arbitrary non-standard model of the theory has that as an algebraically, it can be embedded in it. So now let M be an arbitrary non-standard model. This will add you some additional constants because you've given the, well, I'm saying I want to look in the language what I've named this. And now I want to claim that that model isn't actually admissible. And the reason is, if it is admissible, so I start by pick some non-standard D, and I look at the formula X is not equal to D. And now the I omega rule says if this is true for each given constant, then it's true. And of course, it is because none of those are the non-standard one, right? So you've diagonalized. But on the other hand, since it's by universal instantiation, it's true of all elements. Well, so then D not equal to D is true, and that's not such a good thing. So what I've shown, let me just state it since you just came in. If you add this rule to first order logic, you have the basic language, but you have a language fixed with a fixed set of constants. But when you look at models, you add constants in the way of Robinson's, and you allow those constants to appear as the parameters in the omega rule. And then, other than that, it's the usual omega rule, but the difference is exactly admitting those constants. And then what we've shown is you can diagonalize on, if you take a non-standard element and you diagonalize on X not equal to D, and you see that there are no non-standard elements. And so I started with this as I used Robinson's Q as an example so because everybody's more or less familiar with that particular structure, but the structure had absolutely nothing to do with it. There's no arithmetic actually involved here. You take any theory with countably many constants and suppose that the structures demonstrated by those constructors can be embedded in any other model, then no model of T omega has a proper extension. Oh, I see. I didn't. Right. And when I say this, just suppose you take a different incomplete theory. I have two predicates, red and green. And I just tell you that I have two predicates. Well, now any model, you take any model at all of that theory with these countable many constants, then it doesn't have any extensions, but there's continuum many countable models because I can mix the reds and greens any way I please. Right, now I'm going to switch to the two-sorted version. And so this is really what Henkin and Uri are doing. It's the model theorist version of omega logic. But it stems back from there, and Chang Kiesler have both of them in their model theory book. But what's the omega rule now? It's that if you have but these D's in the standard omega rule have to come from the base structure. If something is true in each, if it's true of all these elements, then it's true inside N. So the only change from the one sorted case is that the conclusion is restricted to be inside N, and the change from our station is in our situation that's still true, but we allow additional parameters that are from the other sort. All right, and now the claim is that I can interpret L omega 1 omega in this logic, as a theory in this logic, and for that we need what's often called Chang's trick. So if you give me any sentence in L omega 1 omega, so remember L omega 1 omega is like first order logic, except I'm allowed infinite disjunctions, infinite conjunctions, and existential quantifiers with a finite number of variables. And so in particular formulas will only be allowed to have finitely many variables. Well, that's the one. Right. So for each infinite conjunction, you add a relational symbol phi of r sub phi of x, and you add the axioms. Phi sub I of x implies this phi, and then you consider the type of having all the phi of I of x's, but not r phi. Well, that type you want to omit, in any model. So just to make this a bit concrete, look at the theory of the integers under order. And so then there's two non-principal types over the empty set. You're infinitely big, or you're infinitely, well, you're still big, but you're going in the other direction, right? And there are types that describe each of those. But you can define the structure with this sentence that says there is no element that satisfies being infinitely large, and there's no element, different sentence, there's no element that says I'm infinitely small or infinitely far away in the negative direction. So when I make this translation to Chang, I'll have the theory of discrete linear order with these two additional predicates, and if I take the atomic model, I will omit those things. So I'll just get all right, and now what I want to do is you will give me a sentence in L omega 1 omega. At some point in here, it's got to be a Scott sentence, meaning it's categorical. There's only one countable model. And I am going to do Chang to it, and I'm going to have this two-sorted vocabulary with N is one side and V is the other. And on the V side, we have the Chang model, a model of this theory with all these additional predicates for the types, and I want to code the types being atomic. So this is what I've said, right? I'm going to have an n+1 area relation so that you give me an n tuple of elements of V, and then there's going to be a constant over here which says R of this point, and this sequence over here is true if and only if they satisfy the atomic formula that that this type does. And now I'm saying in more detail what I just said because I constantly get ahead of myself. Somehow I've left with the I didn't get the footnotes out last night. So this is exactly what I've said. If you have a constant in the Chang language, it becomes a constant in my extended theory. And then this T phi hat actually does this coding. I mean, the coding is essential, but it's built into the. I think the reason I've got this down here is I had to actually do a little work here because both Morley and Chang only did it for one type at a time. And in order to give the argument at the end, I have to have them all coded. So now what's happening is R of CNI X bar means the nth type, the ith formula in the nth type is true of X bar. And I say the nth type because they're all atomic types. We've got. Right, and so this is just saying step by step what I've just summarized, right? Each, for every V0, if you take an element that is related to CNI, then it satisfies the principle. There's some atomic formula that generates that type. And if you take any V sequence, there is some V1 that does code the type. And such a thing is called a G omega model. And now what I want to claim is that the models of this theory are the atomic models of the Chang. But no, now I've gotten away from this business of everything being countable. There will be models of this in every cardinality unless something special is done. Yeah, and so here is actually the exact definition of the rule. Right? If all the constants, all these designated constants, are true of a formula which may have a parameter upstairs, this is the crucial point, then and this VI is something that looks like it's right, that it actually is something that's coded. So this is a kind of a schema that for this rule, because I've got to talk about the coding. And then for all x. And now the diagonalization doesn't tell us that there aren't any points up there anymore. It says that if there's a point up there, well, this is the rule, sorry. If you have something that's true, well, this is the universal extent, yeah, that's the universal elimination rule. I'm sorry, that's the old rule. And then the G omega rule is, I presume, on the next slide, or did I just say it? Oh yeah, I did the omega. There's the omega rule, and here's the elimination. Okay. But now what the diagonalization tells you, that if there's a point upstairs on the V side, it has a code, but that code must be realizing a non-principal type. But it doesn't say you can't have lots of elements upstairs that realize principal types. And that's exactly what the models of the chain theory are. And if there's, what I say is, we have an interpretation of L omega 1 omega into two-sorted first-order logic with the G omega rule. Whether it works the other way, I mean, the problem is, if I knew this G omega thing was complete in the Gödel sense, provable if and only if true, then we'd get this by interpretation. But I don't have any real good idea of which way it goes. So, which structures are categorical? And this is kind of a classical fact in L omega 1 omega. If you have a Scott sentence that has a proper extension, right? If it's isomorphic to an extension of itself, then you do Vought, and you just, well, not a Vought and back and forth. It's just this one has an extension. Oh, but it's the same, so it has an extension. But it looks like this, so it has an extension. You take the union of those after Aleph 1 steps, and you get an uncountable model. So it's from Vaught's Bible. Okay, and now I said I was going to say something about geometry. And that is, so I did this particularly with, well, after all, if you're going to do circles, you ought to have pi. And how do I describe pi? Well, I'm going to add a new constant symbol, pi, and let in and cn be the lengths. We're in a situation where we've made sense of length, be the perimeter of the inscribed in it. And you insist that for every x, 2 pi is between. And so now, if you realize that type, you've got something that's pi. Now, that's a non-principal type. Well, except I could add an axiom saying there is an x that satisfies this type. And so a theory that I think one might argue is what Euclid was actually thinking about is, if you take, well, first I want to say, well, this is just getting pi. You take the postulates of a Euclidean plane, you take a family of sentences declaring every odd degree polynomial has a root. So because the algebraic things, I don't know, maybe he only wants constructible. So whether it's exactly Euclid. I might have to have if I really want to make an argument about the historicity of Euclid, I might want to weaken this statement. But this is just for pi. And as I say, if this field is not, if I've ordered it by, I fixed some field and I'm taking in its first order theory, if I choose it to be if it's Archimedean, then there's only one realization of the type, and so there's only one way you can make this consistent. But I'm going to just change that definition a little bit. Instead of saying this just for pi, well, let me first start with this. So this is from Ian Mueller's book on the The Logic of Euclid or something like that is the title. And he says, one might say that in applications of the method of exhaustion, the limit is given, and the problem is to determine what kind of sequence converges to it. Since in the elements the limit always has a simple description, the construction of the sequence can be done within the bounds of geometry, and the question of constructing a sequence for an arbitrary limit never arises. And I can grasp that as saying, insist first that you're going to just take the algebraic closure of the rationals, and as I was mentioning a minute ago, maybe I really should say the constructible closure of the rationals, and take and add the recursive cuts in the rationals, which will be the, you have a nice description of the, and take the Scott sentence of that countable structure. Now apply our theorem before. I've told you exactly what's in it. It doesn't have any isomorphic extension. So the previous theorem applies. This is a categorical theory that is, quote, Euclidean geometry. I mean, the historical argument is not intended to be taken too seriously. Okay, now the rest of this talk is the more philosophical end about where this comes up with the objection to with the Walsh doxological challenge that I mentioned 2 days ago, and how our notion of a conceptual framework modelism is a reasonable variant. So recall, maybe it's even on the next page, I can't remember. I was copying stuff over last night. No, I guess not. Oh yeah, I do have that. Right. The we have these frameworks. Sorry. So remember, the doxological challenge is, how does a modelist identify an isomorphism class? And we've argued, and I'll say a little bit more about it, this kind of dissolves if you introduce some sort of notion of frameworks so as you can actually make sense of it. When does this act? If you ask this question of the grade school student, what are the natural numbers? The best he can do is what Rodrigo would say: 1, 2, 3, da da da. And thinking about the whole thing, if you have progressed to Almoç's naive set theory, then it's the natural numbers. I have the set, and I can describe it in various ways, by von Neumann or by Zermelo or whatever. Right, and so then and still there isn't, I say naive set theory very surely. The ordinary mathematician is not thinking, I'm going to prove this in a formal logic, and I'm not going to describe it in a formal logic. I give definitions. They're mathematical definitions. What's this logic nonsense? And I'm going to give a description of this conceptual framework modelism that I've talked a bit about before. I'm going to do some more. And I'm going to discuss the circular argument, which is one of the arguments in Button and Walsh, which is that somehow you can't make this definition without already having assumed arithmetic. And as I've made, I think, pretty clear, I haven't said anything that uses arithmetic, and I want to make that more explicit. So this is our current edition of current version of the first section of this So rational reconstruction of the theoretical levels that are constitutive of mathematical knowledge. It's not a sociological description of mathematical practice, but a logical reconstruction of the system of concepts needed to deal with mathematics. For us, as for Carnap, a linguistic framework is a system of linguistic expressions and rules that cover the use of these expressions that are employed when dealing with a certain domain of objects. The meaningfulness of a sentence depends on the framework to which it belongs. Thus, problems may be meaningless in one framework and answerable in another. All right, and the structure framework is informal, natural language, and likewise practicing mathematicians just consider intuitive, pre-theoretic mathematical concepts, such as numerals, functions, the operations that children work with. They grasp these concepts in the process of learning, and then there's this cognitive science kind of research about how this is taking place. There's a pre-theoretic notion of natural numbers along with the addition and multiplication and so on, but you know, you certainly don't say multiplication is what you get by a systematic induction from addition. And we refer to these as pre-theoretic. But and then the theoretical framework of naive set theory. And I think Ramos was really he did this very well. It's and it's what we teach. There's now a common course in the United States called Introduction to Proof for sophomores, and it's taking place in this context. So you define in naive set theory things like individual substructures, individual structures, I don't know where the sub came from, an omega sequence, classes of structures, groups, rings, fields. No need of an entirely articulated, formalized language. And we think that mathematicians have acquaintance by definition or construction. If you now are a mathematician who does give this inductive definition of multiplication, that you have a notion of this thing, right? You had to have the concept in order to build this. Right, and we call this, well, we usually call it informal, but there are, a certain subclass of mathematicians, like, for example, model theorists, who will tell you, oh yes, I'm really working in ZFC. Or today, if I'm Shalom, I need the weak generalized continuum hypothesis, or whatever. And this is, I stuck this in last night. I'm really thinking here about the doxological challenge, which was, how do you identify an isomorphism class? And this is a note by Barry Mazur about why this is an essential notion. This is the way. So, Mazur says, to define the mathematical objects we intend to study, we often, perhaps always, first make it understood, more often implicitly than explicitly, how we intend these objects to be presented to us, thereby delineating a kind of superobject. I'm not sure what Shapiro word you would use for this, but that is a species of mathematic objects garnished with a repertoire of modes of representation, of presentation. Only once this is done do we try to erase the scaffolding of the presentation to say when two of these superobjects, possibly presented to us in wildly different ways, are considered to be equal. In this oblique way, the objects that we truly want to enter the scene are only defined as equivalence classes of explicitly presented objects. That is, as specifically presented objects with the specific presentation ignored, in the spirit of ham and eggs, but hold the ham. I hope that it's not too colloquial in English. If you have this thing at a restaurant where I want this, but leave something out. So the third framework is the meta-theoretical framework of formalized theories in various logics. And here we have the formal concepts defined by a mathematical logician. She's acquainted with them by defining a formal axiomatization of the informal concepts from framework 2, and describes some of those concepts by a formalized logic, a vocabulary, and a categorical set of axioms. So I want to stress this. If I'm going to give categoricity, I've got to tell you what logic, what vocabulary, what axioms. And if only 2 of those are there, the person hasn't really told you what's going on. More specifically, those who work in this framework are directly acquainted with the formal object, the formalized object, and can refer by a formal description to the concept in framework 2 that is categorically formalized. The philosophical framework. Yeah, okay. So this was copied out of the paper at 7 o'clock this morning. So you can see why some things aren't there. In the philosophical framework, it's just that's who asks these questions, and so you can reflect on what's gone on before. And our sort of meta framework system is that as you go up, you have it at your command everything in a lower level. So, again, what is the situation of identifying an isomorphism type? In framework 1, this is a meaningless question. In framework 2, it's obvious. The isomorphism type is the set of things that are, or the class of things that are isomorphic to this object. But it's a real question for framework 3, because then you're supposed to be thinking about it in terms, what's the theory? And the question is, can you find a categorical theory? And of course, in order even to do this, you have to have some kind of concept at the earlier level. All right, and this is in some sense weaker than identifying the isomorphism type in framework 2, because there I just said the things that are isomorphic to this. Here I've got to decide, what exactly is the vocabulary, but I had to do that there. But I didn't have to know anything about axioms. Here I have to find the axiom system, and then I have to actually prove, and I have to also fix the logic. I mean, the whole point of this is that there are sentences that are not categorical in first-order logic. I use the same axiom system plus my new omega rule, and now it's categorical. And so now, I think I said a little bit last time about the first day about Button and Walsh introduced this notion of concepts modelism for the purpose of not thinking about it. They really, everything they say very specifically is about structural model, object modelism. But the term is fine, and we're trying to explain what it means, or our notion of what it means. And it's that mathematics is classical mathematics, a complex process of constructing and developing certain kinds of claims, of concepts. And so we're going to be analyzing those concepts and how they develop and how they interact, which I guess is what I was doing the last couple of days. And it's basically a linguistic thing. I mean, the Plato I'm agnostic about Plato. It isn't essential to it either way here. And again, just thinking about what is the natural number system, and Rodrigo pointed out yesterday, it's notion of iteration, and that iteration, well, now we supply a structure. I mean, we being mathematicians since a long time ago, have a definite way of doing that. I mean, well, extremely definite with Russell, or not Russell, but Zermelo and von Neumann. And now I want to say images are part of this, but they're not the whole story. And I thank Roman Kosak many years ago for pointing out to me, people think, okay, I understand the natural numbers, 1, 2, 3, 4, 5, 6. And so I understand arithmetic. Oh yeah? Tell me the picture for Maslow's theorem. This image is fine for the successor. It doesn't work very well for addition, although maybe not too badly. But knowing what a polynomial looks like, tell me the graph of here's this 5th-degree polynomial. What does it look like? Well, okay, we try to make people in high school, and certainly beginning college, draw a picture of that, but it's not something that comes, and whether it means anything probably has a lot to do with whether you've studied some calculus at the same time and know what increasing in monotone and so on mean. All right, and now the last part of this will be against the circularity argument. And so let me begin by clarifying what the circularity argument. And what is it that they say is circular? Button and Walsh argue that an attempt by a moderate monolist to appeal to a categoricity theorem is an extension of first-order logic. To explain how we grasp a mathematical concept by formal description is hopeless, as one must semantically set forth a logic that will invoke precisely the kind of mathematical concepts that were at issue in the first place, and which they were hoping to secure by an appeal to a categoricity theorem. They consider that advocates of weaker logic than second-order logic must spell out their logics semantically, since these logics are non-compact. And look, our logic is not given semantically, it's given inferentially. And just a little further, this circularity argument is also described by Button and Walsh as a reiteration of the taxological challenge at the level of selecting a logic, because the logics stronger than first-order logic must be characterized by using first-order concepts. They don't really say what the problematic concepts are, but I mean, maybe that's unfair, because they're giving 10 things and sort of saying various things about each of them. But what can be problematic? It can't be finite or countable or inductive definition of formulas, because they're happy with first order. And that's what I'm saying. I call this the you're another. But there's a Latin for this. But you're all philosophers. What's de quoque? And so I'm going to be careful now about spelling out my set theoretic hypotheses to clarify that they're a lot weaker than that. It's a very weak form of logic, of set theory. And in particular, ordinal doesn't appear. Right, we're talking about at least our new rules. I mean, we're building formulas by induction, so it isn't quite fair, but we aren't using it in any way that's, for the quantifier, the ordinal notion doesn't appear. The ordinal notion is cardinal. The quantifier notion is cardinal. Or the omega rule is cardinal. And so, to do this, I go back and I did this partly because of some discussions I had with Matthias and Colin McLarty about the connections between set theory and category theory, and the distinction between McLean logic, McLean set theory, and CFC. And I want to show that you don't need, you don't need replacement, for example. Nothing is very, so I'm going to say a set is finite, and it's Dedekind finite, but if every one map is onto, and it's infinite if not. It's countable if and only it is infinite, and every proper subset is either finite and has the same cardinality as X. That's all fine. Now, that's the same thing as in being embedded in omega. That's a hard theorem, but I don't care about that. I'm not using anything about that in the argument. And so that's what I say. I don't care about. I don't say anything more about that result because I'm not going to use it, and I'm not using choice. And so the argument that Button and Walsh give, and Kerlner gives, and various other people, that they're all based historically, right? The notion of omega rule arose around arithmetic, but our omega rule, and Hunkin and Ory's for that matter, doesn't have anything to do. I mean, it has something to do with arithmetic. You can apply it to arithmetic, but there's no arithmetic needed to state and use the rule. So I do need countable here because I am saying it's a countable language. But then the universal closure, it holds for all constant if specific countable set C, then it holds, then the universal closure holds. Thus our rules of inference depend only on the notions of finite and countable cardinality. Neither the rules of inference nor the truth condition for infinite conjunction or disjunction have any dependence on the notions of well order and induction that aim to be secured by a categoricity theorem for PA or PA omega. And the same thing for the infinite, I put it in there, infinite conjunction, right? An infinite conjunction is not an infinite quartered conjunction. We write it down as the disjunction of phi sub I, but that was unnecessary. It's the index of phi sub A for A in some set capital A. I mean, and that's because that's how the semantics works out, but yeah, and so I guess I keep getting ahead of myself, right? They argue that L omega 1 grasping an infinite disjunction is like grasping the natural number, and I don't agree. An infinite disjunction is derivable from any of its disjuncts, and on the semantic side, the truth value depends on the set of the formulas, not their order. There's nothing, I mean, yeah, I don't see there's any induction in this at all. I mean, except maybe in the same sense that I'm appealing to this notion of what the natural numbers are in talking about the right. Oh yeah, I'm just putting this last. I wrote this down later this morning, and because we have this phrase about just more theory, and I read this in Button and Walsh, and I'm never quite sure what the just means. And maybe people who've read more of Putnam can tell me. It's certainly more theory, different theory at any rate than formulating first-order logic, but it's not just more theory because it doesn't require any new instructions. And maybe that's different from being more theory. I don't know. So I'll pause with that or quit with that. We have time to. Well, we're not doing badly. We've got another 20 minutes. But this time I didn't stop and make you talk. that has something to do with having to put a lot of this stuff together this morning and getting as far as thinking about where can people stop and talk. I didn't get that far. So thank you very much, and let's see if we know anything.
Thank you, Professor. Questions, comments?
Yeah.
Thank you very much. I hope that at some point we can discuss each one of these lines, because I probably have a comment on each one of them. My reading of your proposal is that, in my terms, you are proposing a new basic agreement, which is the generalized omega rule. I am also proposing the same thing, but in a different level, probably. As I see it, you are proposing an inferential agreement, but it is also semantic, because this inferential agreement is used to give you the categoricity that means definition for you.
Yeah.
Right?
Yeah. It gives. Yeah. It determines the semantics because we have the categoricity of the rule.
The new agreement, which is the same agreement that I am proposing, is directly definitional. It is not inferential in my view. I separate the levels.
But it's an agreement about what the rules of inference are.
Yeah, your agreement,
mine is, yes.
Yeah, but my agreement, my agreement is not inferential.
Okay, yours is definitional.
Yeah, my agreement is directly definitional, right? In the sense that we should restrict the class of structures to omega structures, to sorted omega structures in your language, right? We should not interpret mathematics with the class of all first order structures, but just but instead, not just instead, with the class of omega structures. And I think in this way some issues do not appear. So that is one of the points that we have discussed. I am not very much concerned with categoricity, because I am concerned with defining classes of structures. Yeah. And this class may be consisting or containing just one structure. It's okay.
Yeah.
That is where categoricity appears in my framework. We are trying to define a class with only one structure up to isomorphism, and we can do that even without Scott sentences. Well, this is one. I think that this is one point.
Well, let me just here. I'm not. I think you're trying to work a little more generality than I am, but here I'm saying that I have given you a logic such that that is intertwined with L omega 1 omega, and a structure, a countable structure, is categorical if and only if it has this property of being not generative. right, that it has no proper isomorphic extension. And so it's, I use the Scott sentence for that, but I've got a Scott sentence for any countable structure. That's not, and so I'm making a clarification of which structures can possibly be, which countable structures can be categorical.
Yeah, there are more information. There is some more information in this, but I think that the second point now is concerning these objections, and I think you were right, but probably the critics, they are concerned with the following problem. Affinitists could not adhere to the agreement you are proposing. Because just like Hilbert is not a constructivist or an intuitionist or affinitist, but he formulates the formalism, and he says even the intuitionists can live in my foundations, because they just need to forget about interpretation, forget about semantics, and we live in a symbolic life which is finitary, and it really will make very little difference. So Hilbert claims that his philosophical or his foundational program can accommodate the intuitionists, which I would reformulate as saying, well, Hilbert is proposing some kind of agreement to mathematical communication. Well, we in mathematics we will communicate like that. We have strictly finitary symbolisms and formal rules, etc., to communicate, etc. And even the intuitionists can be part of this agreement. Can how do they say in English? Can adopt this agreement, because if you are, or even the Platonists also, because the Platonists will just add some interpretation. I do this formalistic communication, but I am thinking about the ideal of mathematics, the essence of the Platonism, which is the ideal of mathematics. I'm thinking about the ideal. The finitists can also live with us, because they just need to forget about the ideal. It is just the symbolism. Mathematics is about the mathematical symbolism, not about the ideal. And so they can also live with us. Probably Hilbert was a Platonist, but he was formulating things like this. So I see the kind of objection to infinitary omega rule in this way. People who are objecting, and it is not myself, are probably concerned with that kind of exclusion. They are saying, oh, your agreement is excluding some people. So not everybody can have a live in this inferential logic.
Yeah, but right. So, but I mean, the objection is an infinitary rule. and I mean, and that's fair. I mean, there's just, if you're going to say there can't be infinitary rules, then this isn't going to work. And what explicitly is the argument for there being no infinitary rule? I'd like to see that argument, other than, well, we can't follow the argument, but we know we often can, and there's long, a long history of discussion of the omega rule in terms of what sort of constructive steps do you use in allowing the construction and getting different variants of the rule. But I think that this actually is a place where it's just, well, yeah, if it's a yes or no. It's definitely, and I'm just thinking that well, and maybe no one believes this, but my thought was that an infinitary rule is less of a problem than saying you have infinite formulas. And I don't know, maybe there's lots of people who don't think they're the same. I don't know.
I agree with you, because infinite formulas would exclude from the start the finitists, in the sense that I have. So if you are proposing a linguistic agreement in which the expressions are infinite, the finitists cannot adopt this agreement.
Right.
But the objection to the infinitary rule could be formulated in this way: it will does not give rise to a recursive proof system.
Right.
So it is not verifiable, formally verifiable. So formal verification of proofs is a subject that is growing, just like intuitionists grew at some point. Hilbert was concerned with the growing of the intuitionists, so he started trying to accommodate them. And so even if he is not an intuitionist, he proposed, well, our mathematics will be intuitionists, so they can have a life with us, just forgetting the meaning of the expression, of the expressions. And we will have an intuitionistic consistency proof, and we will have a intuitionistic completeness proof, and so on. And so one of the objections that could be raised is just this: an infinitary rule is not verifiable by a machine, and machines are starting to be our mathematical partners now. And so there is an important section of mathematics now that is probably, or in the years to come, that is probably machine mathematics. So they are somehow excluded from the agreement. If we can speak of agreement with machine, which is a very subtle question.
Yeah, I was going to say that in the other end, it's not impossible that you can't find a way to use you're using probabilistic methods to begin with. I ought to be able to put in something about the non-standard elements that you have some certain probability of that, and then you're going to count it. And I don't think this is an insuperable question for any sort of AI. It's not. Doesn't seem to me. Well, it's just that AI is not a clear enough. Since there is no formal derivation involved in AI, the notion that we have to have one seems kind of asking too much.
Well, I don't know if there are more questions, but I don't want to be the only one talking to. And Yeah, another difference that we have already talked about, and and you have explicitly mentioned here. You have adapted Chang's result to omit countably many types at but
Well, I'm not sure. I think, in fact, what I've done is adopted Chang's result to admit only countably many types.
to admit only countably
And whether I think you could have, I have to think about it again, but that you could have a theory that had uncountably many types, and I would be just looking at the atomic models. Yeah, I mean, well, no, let's see. I mean, I was going to say dense linear order, but it is not, well, yeah, I mean, I can study it, right? I mean, it's not generative. And yeah, and so I can write, my general theory can consider dense linear order. It's and then you get uncountably many models. And over, oh, I see, it's out of zero category, so over finite sets you only have countable many, or indeed only finitely many types. I should think about this before, but I don't get a explicit counterexample off the top of my head, but I think this is more what it is. I mean, that's the way I did that quoting in the end. I had started thinking I was going to say something about being non-atomic, and it actually turned out to be an argument that it is every type that's realized is atomic. Yeah. I mean, so do arithmetic. The Scott sentence of arithmetic is also categorical, and then the theorem applies. But maybe there are uncountable atomic models. I guess not. Well, something to think about. It's not.
Yeah.
Well, you aren't. Yeah, I mean, you aren't going to get. Yeah, you aren't going to get categoristic. Let me just stop blithering and.
Okay.
Yeah.
We can discuss more about this. Yeah, but this admission of only countably many types is to guarantee categoricity.
Well, no, it's not to guarantee categoricity. That's the point. That the countable many types guarantees the that you have the model of that you have an atomic, that every model is atomic. But if I take if I take an algebraically closed,
countably many.
Well, I mean, yeah, if you take well, no, I mean, it's omega stable, so I'm getting, but if I simply take take the theory of the real theory of a real closed field, then that's first order action. But I certainly have a complete. I have a Scott sentence of, say, the real closure of the rationals.
The algebra.
Oh, I see. When I say, if I say the real closure, then I have to have something where there's. I want to take the Scott sentence of something that has uncountable models, and then when I do, this result will still, the translation will still work. It just won't be. So take the, and then, oh, that's right, because the atomicity only has to come after I've changed. So take the theory of a saturated model of a real closed field of an algebra. Then its L omega 1 omega theory will work on for this. You'll get you'll get a Chang theory, but you'll get all the models of real closed fields. And then there are types that are living there. They just aren't. The models are all the atomic models. And now I have to think about whether there are really atomic models of. They've got to be. Oh, because they're atomic, not in the. They aren't atomic with respect to the field language. They're atomic with respect to
new predicates.
The new predicates. Yeah.
With the predicates for types.
Yeah.
Okay.
Yeah.
Questions? No. Oh, thank you again,
Yeah.
Professor.
Thank you.
So thank you, Rodrigo, again for your lecture in this mini course defined in mathematics.
Thank you, Hugo. Let me just close. So we have concluded in the last talk our more or less our philosophical framework, which is not historicist. So we believe that mathematics is forever under construction edifice, but it is not a matter of historical accident. So mathematics is under construction, but historically, but it does not mean that it is a result of history only. So mathematical practices are aimed at knowledge. That was part of my conception of mathematics. So mathematics is a collection of practices. Mathematical practices are aimed at knowledge. They comprise the practices of definition and truth, and they are governed by formal axioms and rules that are formal agreements. So we agree on the formal axioms and rules, and those who are participating in the agreement are doing mathematics. Therefore, in spite of the open texture of mathematics and the standards of definition and proof, we believe that the general lines of our understanding are likely to remain applicable even if mathematics is changing. So now I would like to give some mathematical logic theory of definition, or the outlines of a mathematical logic theory of definition, and I will focus on the theory of standard first order definitions. So if we have time tomorrow, I will talk a little bit about what are the differences between first order definitions. I have already said something about this, and the differences between first order definitions and omega logic definitions. But nevertheless, it is very important to study first order definitions because they show us the theory of first order definitions show us the path to omega logic definitions also, and to other theories of definitions. So an important notion in first order definability theory is the notion of p-partial isomorphism. So we have, in mathematical logic we deal with, we are here dealing with first order structures, right, which are domains with designated predicates. So we have a domain and we have this special predicates attached to the domain, and the way we compare structures usually are in terms of isomorphisms. So this is the definition that is behind the uniqueness, or what does it mean that two first order structures are essentially or are equivalent as first order structures, or they are essentially the same, is that they are isomorphic. Now, the answer to this question is that they are isomorphic. the usual answer. But that comparison between structures is very much restrictive or very strong. So if two structures are isomorphic, they are really the same structures. The same structure. They are instances of the same structure, let's say. So we need some weaker versions, because many times we are comparing structures which are not isomorphic but are similar in some sense. And so the notion of partial isomorphism is a weakening of the notion of isomorphism, and p-partial isomorphism is also a weakening of the notion of isomorphism. So let A and B be sigma structures, in which sigma is a finite sigma. That is a finite set of predicate symbols, or a finite sequence of predicate symbols. And let A bar and B bar be n tuples in A and B respectively. That is, the finite sequences of individuals. We say that the pairs A bar, and B bar are P partially isomorphic, or if there is, or P equivalent, if there is P partial isomorphism F from A to B, sending A bar to B bar. What is a P partial isomorphism F from A to B? Well, F is a partial isomorphism. What is a partial isomorphism? It is an isomorphism, but that is restricted to a finite part of the domain. So it is also called local isomorphisms. So we do not require that the whole domain of A is in the domain of the domain of the isomorphism, just a finite subset of it. And so F is a partial isomorphism in this sense. Partial refers to this restriction of the domain. And P is the number of times F can be extended by the back and forth condition. So F is a partial isomorphism. F matches A bar and B bar, and F can be extended at most P times using the back and forth condition. What does this mean? That you can add at most P elements to the domain, or to the range of F, still having a partial isomorphism as a result of this extension.
What really means at least P, because when you extend it the next time, if it says you at most, then you can't make the next extension.
Which can be extended at most P times.
But you see, what I want to do at the next stage in the construction is find a P plus 1 partial extension.
No, I will find the P minus 1 partial isomorphism. When I extend F to G, G will be P minus 1.
When I do the back and forth construction, I have an A bar and a B bar, and then you give me an AN plus 1, and I find a BN plus 1 going up.
Oh, yeah, you extend, you add A to A bar, and but you do this addition at most p times. You can do this addition at most p times. So you have a bar, and then you add some a1.
Yeah.
And then you can again add a2. This can be done at most p times. So you add ap and then you must stop.
I don't know, I mean, the way, if I want to show, if I'm doing the errand point game, I want to be p, I suppose it's larger and larger p's. I mean, you can say something about being only p, but that's not, the elementary or thoroughly equivalent is to be pi, to be, have a p partial isomorphism for every.
For exactly, yeah.
And that means that the guy that at the pth stage, I've only exhibited a feedback.
Yes.
It's not going to be elementarily equivalent if somehow.
Yeah, surely. A and A bar and B bar are not here required to be elementary equivalent. They are just P equivalent, not elementary equivalent.
The other question was, how important is it for you that you have a finite signature and that it's a relational language that has so that we in a finite rather than finite?
Yeah.
So, yes, I. It's just I wasn't talking into it. Sorry. Yeah. So the second question was, do we want to have? Can we have an infinite language, and can we have can we have functions? Because I'm going to do that. So
yeah, you can have infinite signature at some points. The finite signature is used to construct the characteristic formulas. So it is used in the converse of Freire first theorem, and to obtain Freire definability, explicit definability theorem.
Yeah.
So to construct single formulas, we need single characteristic formulas, which is a characteristic formula giving the type restricted to P of A bar.
Yeah. Okay. Yeah. For A, you're gonna to get categorist, you have to do this. It's not. Okay.
So we have here Freire theorem first part. So this first part, it is not the affinities condition is not required. If there is a P partial isomorphism between A bar and B bar, sending A bar to B bar, matching those sequences, and phi is a first order formula of quantificational rank at most P, in which no variable other than x1, xn is free, then A bar and B bar agree with respect to phi. Either when I say that these structures with the corresponding assignment of variables, A bar, B and B bar, agree with respect to those phi's, I am saying that either they are both false or they are both true. They cannot have distinct truth values, false in A and true in B, and so on. So they agree. The n-type of A bar is the set of all first-order formulas, like that, all phi's, like this one, but with unlimited quantificational rank. Forgot about this quantificational rank. The n-type of A is the set of all first-order formulas with free variables contained in the list that are satisfied by A bar in the structure A. This is not in any way finite or limited in quantificational rank. An n-type, I mean by an n-type of some n-tuple, which means that an n-type is always consistent. By the n-type of A bar restricted to P, we mean the subset, the part of the n-type. So the n-type goes across all quantificational ranks. So if we restrict the quantificational rank, which is the degree of the formula, it is similar to the degree of a polynomial. There's the degree that according to which we classify first-order formulas, at least for definability theory. So just like polynomials are classified in terms of degree, first degree, second degree, formulas are classified by the quantificational rank and the number of variables, free variables. So by the n-type of A bar restricted to P, we mean the n-type considered just up to the quantificational rank P. And the finite signature will imply that this part of the n-type can be captured by a single formula. So those are the characteristic formulas. So a characteristic first-order sigma formula, quantificational rank P, and with n free variables, is a formula psi such that for any first-order formula phi with the same quantificational rank and free variables, either psi implies phi or psi implies not phi, or both if psi is unsatisfiable, right? Under the assumption that sigma is finite, so here is the relevance of this, given two natural numbers n and p, there is a finite set gamma and p of characteristic sigma formulas of quantificational rank P and with n free variables, which is a complete set of characteristic formulas. That is all, we have infinitely many types of n types in general, but if we restrict the quantificational rank to a certain P, then there are only finitely many n types up to P. In the case of a finite signature, right? This means that given any pair A bar, there is exactly one psi in this set of characteristic formulas such that A bar is in this state. So you can read the formula psi the formulas psi as the possible states of rank P, or rank P states. So what are the possible states an n-tuple can be? So these are the characteristic formulas in gamma, and there is a finite number of states in this case. So the characteristic formula of the pair such that this holds. And furthermore, if B bar is also in the same state of A bar, then the n-type of B bar restricted to P equals to the n-type of A bar restricted to P. That is, psi captures the n-type restricted to P. The n-type restricted to P is still infinite, but it is, let us say, finitely axiomatizable. There is a finite, there is a single formula that generates the type up to P, or restricted to P. These formulas are similar to the propositional logic, to the lines of the truth table. So the formulas P and Q and R. So this formula is a characteristic formula for all propositional formulas with P, Q, and R for this signature. So Freire theorem, second part. I will not show the construction of the characteristic formulas, but it can be done. Well, for all numbers N and P, for all pairs A bar, B bar, if there is a characteristic formula such that both A bar and B bar are satisfy this formula, which means that both A bar and B bar are in the same state up to P, then A bar and B bar are P partially isomorphic. So if A bar and B bar are P partially isomorphic, then they agree with respect to all formulas of quantificational rank up to P. The second part of Freire theorem, it is an exercise to prove this by induction on phi. Right? So you can do this exercise. One exercise of the course. I will give many. You must do this. The second part of Freire's theorem gives the converse. If A bar and B bar agree with respect to the same with respect to all formulas of quantificational rank P, then they are P partially isomorphic, right? This is an exercise up to the definition of the characteristic formulas. Now, if I give you the definition of the characteristic formulas, then it is not hard to prove this. The hard part is a definition, as in many places in mathematics. So the hard part is what is the appropriate definition of the characteristic formula. So, and our formulation here, right, is not that A bar and B bar are required to agree with respect to all formulas of quantificational rank P, or all quantificational rank P formulas, but they must agree only with respect to the characteristic formulas. So if they agree with respect to these formulas only, then they agree with respect to all, and they are P partially isomorphic. Now we must define what is explicit definability of a predicate in a class. So first, what is a predicate in a class? By an n-ary predicate in a class of sigma structures, right? The predicate is supposed to be defined in the class of sigma structures. So we have a class K of sigma structures. So we may have some structure A here. So a predicate O is a function, a class function, right? So O takes one such A, and I write it this way, and and assigns to one such A set of tuples. So A bar prime, I don't know what set it is. So an arbitrary set of tuples. It is the extension of the predicate in the structure A. So if O is an n-ary predicate in a class K of sigma structures K, then O is explicitly definable if and only if there is a first order formula phi such that for each structure A in K and each tuple A bar in A, so A bar is in the set, in this set of tuples that O assigns to A, if and only if A bar satisfies phi in the structure A. So phi is defining this set. It is saying which it is phi can be seen as the criteria to belong to the set. So when a tuple belongs to the set, when it satisfies the criteria phi. So phi, but phi is a formula, so it is a definition of the extension. And this must hold uniformly for all structures A in K. So which predicates are definable? That's the question. Which ones are definable? So here is the definition of definable, but which ones are definable? How can I get a predicate, look at it without, well, because a formula is something that is not in the predicate. It is something external, language, stuff like that. The predicate is just a function on a class of structures, assigning tuples to the structure. So that is our problem. So R, if R is a new symbol supposed to name a predicate symbol, is a predicate name. Most of our symbols, most of our semantic notions are naming notions, right? So a predicate symbol is a name for a predicate. So if R is introduced as a name for the predicate O, and this is the expansion of A. This pair is expanding the structure A with this new predicate interpreting R. And if T is the set of all sentences in this expanded language valid in all expansions obtained from structures A and K, then O is explicitly definable in the above sense if and only if there is a formula phi such that T and phi explicitly define R in terms of sigma over the class of all structures. This is not very important, just a remark that this notion of explicit definability intersects with the notion of explicit definability inside a theory. So we are talking about explicit definability with respect to an arbitrary class, which may not be an elementary class. So not mine. So we have said what it means to be definable. When a predicate O is defined by, explicitly defined by a formula phi. On the other hand, O is preserved under P equivalence or under P partial isomorphisms if and only if for all structures A and B and for all n tuples A bar and B bar, if there is a P partial isomorphism between matching A bar and B bar, then A bar is in the predicate O if and only if B bar is also in the predicate O. That is, the predicate, we say usually in mathematics that the predicate is invariant under P isomorphisms or P partial isomorphisms. Not all predicates, of course, are invariant, right, under isomorphisms or under P partial isomorphisms either. But those that are important for definability theory. So Freire says definability theory is the equivalence between P invariance, so invariance under P partial isomorphisms, and definability. Right? It says that a predicate O, right, is explicitly definable if and only if O is invariant under P partial isomorphisms. So we have here an answer, right? A useful answer to our question: which predicates are explicitly definable? The ones that are invariant. Why this is interesting? Why? What have we gained with this equivalence? Right. I have mentioned that to be explicitly definable is something that it is not in the predicate itself. So you will not find the explicitly defining formula phi just looking at the predicate or just operating with the predicate in some way. But this notion of P invariance is much more intrinsic to the predicate. So predicate is P invariant if you look at this is part of the predicate, right? So A bar is in the predicate, B bar is in the predicate. We are not using something that it is outside the predicate. So you take A bar and B bar. If they are P partially isomorphic, you look at the matching between A bar and B bar, and you ask if this matching is a P partial isomorphism. And then you look if this equivalence holds, so for all A bar and B bar. So this is in principle an intrinsic feature of the predicate. And so this answers the definability question. So it is definable, O is definable if and only if it is P invariant. So invariants under isomorphisms are rarely enough for definability in the first order setting. The structure may not have enough automorphisms or isomorphisms to give definability. So this notion is important because of this. So assuming Freire first theorem, second theorem, this is an exercise. Do the exercise. Exercise 2. Now, partial isomorphisms, not P partial isomorphisms. If there is a non-empty family I of local isomorphisms, so from or partial isomorphisms in the old sense, isomorphisms between finite parts, with the unlimited back and forth property, then we say that A bar and B bar are partially isomorphic under I. So this relation is in fact stronger because than P partially isomorphic because of the unlimited back and forth property. So this is denoted by this. So in first order definability theorem, the problem in many cases is to construct an appropriate isomorphism, a total isomorphism between structures. We want to construct some suitable isomorphisms between maybe models of structures and so on, models of some theory and so on. And the partial isomorphisms provide a technique of constructing global isomorphisms by approximation. So in this case, in some cases, this approximation may not converge to an isomorphism, but in some cases it may converge, right? And so Freire isomorphism lemma gives us a case in which the approximation by partial isomorphisms converge to a global isomorphism. And the case is when structures are countable. And here I don't need sigma to be finite or not to have function symbols. And this is not required. The problem with function symbols is that when you add function symbols, you have infinitely many terms and then infinitely many atomic formulas already. And so it also blocks the characteristic, the finitely many characteristic formulas, so it blocks explicit definability by a single formula. But if you restrict the terms to a certain, if you say, we will allow only finitely many applications of a function symbol, then you can have sort of a control also that yeah, something like that. Hodges deals with this case. But this isomorphism lemma does not require anything, so it holds for arbitrary signatures. If A and B are countable and they are A bar, and B bar are partially isomorphic, not P partially isomorphic, but not P partially isomorphic for all P, there's not the same thing also, but partially isomorphic in the same of unlimited back and forth. And so then there is a global isomorphism, F from A to B matching A bar and B bar. This is exercise also. It is similar to Hausdorff's proofs that two countable total densely ordered sets without endpoints are isomorphic. So we want to build appropriate isomorphisms in definability theory, and we have seen a bit why with Freire machinery, but how to do that, right? In model theory, we do we prove the existence of isomorphisms in many cases like this. In model theory, we construct models. So we must reduce the problem of constructing isomorphisms to the problem of constructing models. So we formulate a theory which talks about two models, a pair of models, U and V. And this theory also talks about some relation between U and V, right? Which may be directly the isomorphism relation, or it may be the partial isomorphism relation. Partial isomorphisms are much stronger than P partial isomorphisms, but they are still weaker than total isomorphisms. So we can construct theories that talk about two structures. What is this structure? Well, how I do that? This is a theory that lives the symbolic life. The structures are in the interpretative life. How can I talk about structures within the theory? Well, of course, this is a predicate symbol, giving the domain of the structure. And then you can relativize the predicates to this domain. Similarly, V, it is a property symbol that gives you a domain. And then you can relativize the predicates of the signature of T to these domains. So you have this structures in the interpretation. And then you can say that there is a p-partial or an isomorphism or a partial isomorphism relation or even a p-partial isomorphism relation between them, right? And then how do we reduce the problem of constructing isomorphism to the problem of constructing models? Well, we build this theory, for example, and then show that it is consistent, right? This is what I call codifying isomorphisms. But this hardly works this way. So we may build a theory to codify this instead, right? And then we also show that it is consistent. But then it will give only a partial isomorphism between these two structures, which can satisfy axioms. Here T may say that U satisfies some axioms and V satisfy axioms. So it can say that both are algebraically closed fields. Well, but we have Löwenheim calling. So we can say that T is consistent and T has a countable model. But in a countable model, this U and V are both countable and they are partially isomorphic, and so they are isomorphic. So, but this also works in some cases, but not always. So we built something weaker that says that it is P partially isomorphic, and then by compactness theorem, we use the compactness theorem to show that this, the consistency of this, reduces to the consistency of something like this. The consistency of unlimited back and forth by compactness reduces to the consistency of finite back and forth relations. And then we can, using the compactness theorem, prove the consistency of this, implying the consistency of this, and then by Löwenheim-Skolling, implying the consistency of this. This is behind this Venonio's definability theorem, Beth's definability theorem, Lindström's characterization of first-order logic, Robinson's joint consistency theorem. So all these results can be proved by this technique, right? The core of first-order definability theorem, Craig interpolation theorem. So this is our way in definability theory here. So first-order definability theorem aims to provide syntactic characterization of structural relations like isomorphism, partial isomorphism, etc. through appropriate first-order theories. This is the picture that I have given here. Using these characterizations, a problem of existence of models satisfying some prescribed structural conditions like these models may be reduced to a satisfiability problem, so the problem of showing that this is consistent. For which the basic techniques of model theory can be applied. The basic techniques that I mentioned, compactness and Löwenheim-Skolling, together with the Freysian machinery. So let sigma be a signature. How do we construct such theories? Let me show the simplest case first. Let sigma be a signature and sigma 0 be a subset of it. typically sigma 0 is a finite or the numerable subset of sigma, but not always. So in order to codify the appropriate isomorphism relation, consider the signature obtained from sigma by the addition of two unary property symbols U and V. That will be the domain of the structures, codifying sigma structures with isomorphic sigma 0 reducts. Okay? Because also the isomorphism may not be relating the whole structure, but just a reduct of it. This is in Beth's definability theorem. You have some predicates, and you want to know if one predicate is definable in terms of the others. So you must look if this predicate is invariant or determined by the others. That is, if you take an isomorphism that is an isomorphism only with respect to the other predicates, then it is also an isomorphism with respect to the additional predicate. So we have this reducts. So with isomorphic sigma 0 redux and a binary relation symbol F codifying the isomorphism from U to V. So this is the theory. Sometimes we want the isomorphism to match to a given and tuples denoted by Z bar and W bar, and this can also be included in the codification. So let TF sigma 0 sigma Z bar W bar, this will be T, be the first order theory characterized by the following set of axioms. Axioms saying that U and V codify non-empty structures. These are the axioms. They are non-empty. Axiom saying that F is the graph of a bijection from U to V. So this says for every X, for every Y, Fxy implies that X is in U and Y is in V. So this is the graph of the function F from U to V. Moreover, for every X that is in Y, for every X here, there is a unique Y such that Fxy. So for every X in the domain, there is a unique element in the range that is in the graph of the function. This is another axiom. Right. It is a first order axiom, right? No problem of writing it. And for every Y in the range, there is a unique X in the domain such that, so we have a bijection. It is a surjection and an injection. Now, axioms saying that F is the graph of an isomorphism between sigma 0 structures. We may not want U to be a whole sigma structure. It may be some subset. It is useful to have this reducts. Well, how do you say that? So for every X bar, Y bar, if X1 maps to Y1 and XM maps to YM, this is saying that X bar maps to Y bar. Then the relation symbol R is preserved for every predicate symbol in sigma 0. So if sigma 0 is finite, those are finitely many axioms, one for each R. If they are infinite in number, so we have infinitely many axioms in our theory. And moreover, axioms saying that F matches Z bar and W bar. So it may be useful to have this. So we have here axioms saying that Z bar are in the domain, the Z bar elements are in the domain, and axioms saying that Z bar maps to W bar. Nothing very hard. So we have this lemma, exercise 4. If, yeah, no, for the end of the class. Yeah, for tomorrow, can bring it to me. If this is a model of our theory, so I have not defined the model, so but yeah, this theory has a Z bar and W bar as free variables, and so a model of it must include an assignment for the free variables of the theory. And this assignment, the assignment is this: A bar is assigned to Z bar and B bar is assigned to W bar. Right? So if this is a model of this, then the interpretation of UC is the interpretation of U, the extension of U in C, and VC are domains of sigma structures, A and B, respectively. Why? Because this is a relational signature. So any set defines a substructure by relativization. We need only to intersect the predicate with the set. We need not to close the set under functions because there are no function symbols. So U, C, and VC, which are the interpretations of U and V, are domains of sigma structures, A and B, respectively. And FC is the graph of an isomorphism from the reduct of A to sigma 0 to the reduct of B to sigma 0. And this isomorphism matches A bar and B bar. Conversely, for any pairs of sigma structures and tuples, A in bar and B bar, if F is an isomorphism from the reducts, reduct of A to the reduct of B, sending A bar to B bar, then if we join everything, A bar, B bar, and the graph of F, we have a model of this theory T. So this theory T is codifying this situation. It is codifying two structures with two sigma structures with an isomorphic reducts and along with the isomorphism. If you show that, if you add to this theory, so this is a very, this theory, it is very, it is saying nothing about A and B, right? If you add axioms saying that, for example, A and B are linear orderings, and you show that this theory is consistent, the resulting theory is consistent, then you have shown an isomorphism between linear orderings. So you have constructed such a thing. now we may not only want to codify isomorphism, because this is the last step, and it hardly works.
You haven't finished, right? You told us how to code particular finite subsets. I was waiting for an application of compactness to get the isomorphism model.
Yeah, of course. This comes in the next line.
Okay.
So we have to do that. We have to codify partial isomorphisms. So how we will do that? We codify this instead. So we want to prove that that theory is consistent, right? Instead of doing this, we will prove that this theory is consistent, and then that theory is also consistent because of Löwenheim-Skolling. And to show that this theory is consistent, we will use compactness, and I will show how. So, how is this theory? Now we will not codify an isomorphism between structures, but a partial isomorphism family. Let me show this. Codifying partial isomorphisms. For characterization of partial isomorphism, we have almost the same setup. So sigma, two property symbols U and V, codifying sigma structures with isomorphic redux. This is the idea. And an infinite sequence I1, I2 of predicates codifying the partial isomorphism I. I is a family, right? I can be seen as a countable family of isomorphism relations. I will show how this is. It is by the by the arity. So back and forth property implies this notion of approximating isomorphisms implies growing in arity. So we need a family of predicate symbols. So, it is also important to include the Z bar and W bar in this situation. So the predicate symbol IM is a 2M array. Is 2M array. So and codifies the set of partial isomorphisms matching 2n plus m tuples S and S bar. So this n here will be fixed to Z bar, and so that is why we need just to consider the 2m tuples here, because these are fixed. Such that the n tuples S1, Sn until n S is Z bar, and until n S prime is W bar. So I will give you the theory now. It is much more complex. So we have also axioms saying that U and V codify non-empty structures. This the same. We have also an axiom saying that Z bar is in U and W bar is in V. This nothing new. And now for each natural number M, axiom saying that IM codify a set of partial isomorphisms from U to V and extending the function matching Z bar and W bar. So this is what it means. So for all X bar, for all y bar, I am x bar y bar means that the idea is that I am x bar y bar means that z bar together with x bar maps to w bar together with y bar, and this is a partial isomorphism. This map is a partial isomorphism, and so if this holds, then x bar is in U and v bar y bar is in V. Partial isomorphism. Moreover, all atomic formulas are preserved, saying that it is partial isomorphism between z bar x bar and w bar y bar. So if we replace x bar to y bar and z bar to w bar, the atomic formula phi is preserved, right? So this replacement is a partial isomorphism, the definition of a partial isomorphism. The domain of the replacement is just that. Is x bar, z bar. This is the domain. And now you know. And now axioms codifying the unlimited back and forth property. So for every x in U, there is a y in V such that x to y is a partial isomorphism. For every y in V, there is an x which is in U such that the replacement of x by y is a partial isomorphism, and together with x bar and a bar. So we are trying to say that z bar, we are trying to say that this is a partial isomorphism. That is, for every x in U, I can put the x here, and I find some y in V such that I can put here, and have still a partial isomorphism. And conversely, for every y in V, I can put it here, and then I can find some x in U, and I have a partial isomorphism. So for two, so this is the condition for one, and for extending it again, I say that for every x1 and y1, if I already have one extension with x1 and y1, then given x2 in the domain, I can extend one step further with x2 and y2, and similarly the back condition. This is the fourth, and this is the back. If I had already extended one step, then for every y2 in the range, I can find some element in the domain such that this double extension is still partial isomorphism. And, well, etc. for M. This is the axiom for M. Nothing. Well, Poisson writes something like this in his book, but it is wrong. In the book by Poisson, the axiom, both in the French edition and in the English edition, I have checked both, and they are wrong. It is not a separate lemma. He is trying to prove the Svenonius theorem. You can look at it. He says that these are equivalence relations, which are not. They are not symmetric, not everything. And he makes more than one mistake in this axiomatization. So this is the right version. You can check it. And then we have the partial isomorphism characterization lemma, which says that the resulting theory obtained by the resulting theory is this. We have axioms saying that U and V are non-empty, axioms saying that Z bar is in U and W bar is in V, axioms saying that this codify partial isomorphisms. That means that the atomic formulas are preserved, and axioms codifying the limited back and forth property. Now we have the lemma. This theory, indeed, the lemma that exercise 5, this theory indeed codify the partial isomorphism relation. That is, a model of this theory. If C, A bar, B bar is a model of this theory, then we get the interpretation of U and the interpretation of V are domains of sigma structures by relativization. We are working with a relational language, and the matching of A bar to B bar is a partial isomorphism. Furthermore, if this are in the interpretation of the predicate, then this is this and this, the matching between this and this is a partial isomorphism also from A bar to B bar. If we take the union of all these sets, then we get a non-empty family of partial isomorphisms from A n bar to B bar with the unlimited back and forth property. So now I can address the question by Professor John. How do we use compactness to prove that this theory is consistent? So these are infinitely many axioms. So it is enough to prove that a finite part of it up to M, that is, we can forget this part here, is consistent. But in order to do this, we need only this. In which P is a function of M. Don't know which, but we can calculate how many times. That is, I think M plus 1 or just M. I don't know exactly how. It may be just M, plain M, but not to make a false statement. Let us put here P. Some P appropriate. It may be just M. We'll give the this. And to prove that these are P partially, that there are these structures with the P partial isomorphism, sometimes is given in the problem, right? In the usual model-theoretic problem. So we use compactness in this way. And then, using compactness this way, showing that only a finite part here is consistent, that is proving that this theory instead is consistent, we get the consistency of this, and then Loewenheis-Kohling, we get the consistency of this. And that is why Lindstrom first theorem says it appears compactness and Loewenheis-Kohling and the conditions of the theorem. First order logic is the maximal logic satisfying compactness and Loewenheis-Kohling. Why compactness and Loewenheis-Kohling? Because of this. Compactness allows us to pass from this to this, and Loewenheis-Kohling allows us to pass from this to this. And
what are we actually trying to show? What two structures are you trying?
This is very general here. It's just a lemma. It will be used in many situations.
But
for example,
I mean all these characterizations are that's fine. And yes, I can do this, but the way how is this?
Yeah, of course. Let me show some.
Usually I would just do an induction through the length of the structure.
Yeah, but
why is this?
Well, let me show you an example. It is Venonius definability theorem. You have a structure A and relation R. The hard part of the proof, the Venonius definability theorem can be stated in the following terms. R is definable in A explicitly, if and only if in all elementary extensions of AR, R is invariant under automorphisms, right? So we want to show the following, the hard part. If R is not definable in A, then there are two elementary extensions B R B and C R C with an no, I'm sorry, this is for Beth's definability. So we have one elementary extension B R B and an automorphism, and so we can draw indeed as two we have here. We can think of it as two structures, but it is the same. They are the same. Not C, but B. With an automorphism F such that the function, in fact, is an automorphism of B but R is not preserved. Right? So we have here the reduct thing. Is an automorphism of the reduct this to this part. And we have two structures here in the well, it is one, but yeah. Yeah, okay, but this is, and so we can build to show this. We take the theory Ti. We will construct this theory Ti. Let us say sigma 0 is just the signature of B, of A, and sigma is just sigma 0 plus R. And we have elements, maybe some A bar here and B bar here, such that some X, Z bar and W bar. So we have this theory plus elementary. We want to construct this. So the elementary diagram right. We know in the bottom model that R is not definable. R is not definable. That is the information that we have. And we add the axiom saying that U equals V equals everything. Equals everything. And we add axiom saying that Z bar satisfies R and W bar does not. Right? If we show that this theory is consistent, we will get a partial isomorphism here, sending A bar to B bar, and A bar is here, B bar is not here. All right? And if we get countable extension, then this partial isomorphism can be taken to be an isomorphism. But it cannot be countable if A is not countable, right? However, we are just trying to prove the consistency of the theory, in fact, of the theory of isomorphisms. We are only trying to prove the consistency of this theory, which is TF. We are trying to prove the consistency of this theory. So the consistency is something reduced to finite in many parts. So we will use a finite part of this. So we can assume that A is countable. We can assume that A is countable because we only use a finite part of the diagram to prove the consistency. And so we can assume that everything is countable. And then to prove the consistency of this directly will not work, so we prove the consistency of this, assuming that everything is countable. And then we have a countable model because of the countable language. And in the countable model, if we have the partial isomorphism, we have an isomorphism matching A bar and B bar. And how do we prove that this theory is consistent? Well, the definability, the undefinability of R is used to show that this is consistent with the elementary diagram. This can be this stuff is consistent with this, and we prove that only a finite part of this to prove that take a finite part of this. So we need to construct a P partial isomorphism only, and but this is are models of the same theory, the same model, and so we can show that they indeed are because of the undefinability of R. They are there can be a P partial isomorphism. So there are some technical. My book contains all the details, but it is in this way that we apply. For example, this is one example of application of this lemma. There are many. So you are trying to prove the consistency of this. Then you reduces the problem to the consistency of this. And then you use compactness. By Loewenheim scaling, the problem is reduced to the consistency of this. And by compactness, it is reduced to appropriate P partial isomorphism to show that there are some structures with P partial isomorphisms, and this is as a consequence of the hypothesis that R is undefinable. No.
In the bottom model, it's undefined. So there is a counterexample in the bottom model, but you can still build the partial isomorphisms because you can somehow avoid the
because in the bottom model here there is no definability of R. So in the
you have no need to preserve R.
Yeah, there's no requirement to preserve R because in this elementary diagram there is no definition of R here.
Well, and there's no predicate R.
No, here we have the predicate R, right? But
but the sigma 0 is without the R, so that's your definition.
Yeah, the sigma 0 is this part.
Yeah, and so the back and forth just knows nothing about R.
Yeah, the back and forth is about sigma 0. Yeah, it knows nothing about R, so it does not need to be preserved.
And then there'd be an elementary extension, or every elementary extension.
There will be one elementary extension satisfying mismatching or not preserving R with an partial. I can prove Svenonius, Beth, Lindstrom, Robinson, Craig with this. So, and I have used this together with Lucia to prove the result on minimality of first order logic also. Now we have that's Ebbinghaus also remarks something like this in Ebbinghaus. Two other lemmas, of course, compactness and Loewenheim scaling. This exercise now has the following condition. Each one of you must come with a different proof. I don't want equal proofs of the compactness. You can prove it by ultra products, by the canonical model construction, by Boolean variant models, by there are many proofs. There are many proofs. Topological proofs. Tikhonov. I don't know. Similarly, Loving High Schooling theorem. I only need the weak version, which is the first, but more generally, if sigma is a countable signature, then every sigma structure contains a finite or denumerable elementary substructure. Well, yeah, there are some. I think that I will stop here. It is a good stopping point, and we will continue with this tomorrow.
Okay, thank you.